now. Okay, welcome everyone. We're very happy to have today as our Astroparticle Center speaker, Denise Boncioli from the University of L'Aquila in Italy. Denise did her PhD at the University of Rome. And then she was a postdoc at the INFN in Gran Sasso in Italy. Then she was a postdoc at Desi Soiten in the NUCOS group, my old group in Desi. That's roughly where I met her. Then she went on to Gran Sasso again, where she was a postdoc, and now she's a researcher at the University of L'Aquila. Denise is an expert in ultra-high energy cosmic rays, especially in the propagation of cosmic rays in extragalactic photon fields. She authored the SIMPRObe propagation code. It's a Monte Carlo cosmic ray propagation code. She's worked on state-of-the-art calculations of interactions of ultra-high energy cosmic ray nuclei, including photodisintegration and nuclear decay chains, and comparing the results to actual cosmic ray observables. She's also worked extensively on the neutrino fluxes coming from the ultra-high energy cosmic ray interactions, in particular in modeling that what comes from GRBs and active galactic nuclei. Denise has received recently a Marie Curie Co-Fund Fellowship. I think that's the one you're working on under L'Aquila. And she has a long association with the Pierogi Observatory, which is a member. And she will talk today to us about the latest results from ultra-high energy cosmic rays, including those from Auger. Everyone, be welcome to ask your questions during the talk. You can either raise your hand or write in the chat, and there will be also time during and at the end of the talk to ask more questions. Thank you, Denise.
Thank you so much, Mauricio, for the introductions, and thank you also, Irene and Marcus, for this kind invitation. I hope at some point to be able to come in person to your institute to meet all of you. So I'm going to talk about, as Mauricio said, the latest results in the ultra-high energy cosmic ray physics and about their interpretation. So I'm going to list more or less the results of the Pierogi Observatory, since I'm a member of this collaboration. And I will try to do this with the aim of the understanding or the improving the understanding of the sources of the ultra-high energy cosmic rays. So I hope to see that you are seeing my second slide now. That is working, okay?
Yes.
So yes. That's the outline of the talk. I'm going to do to give an introduction, and I'm going to talk about the interactions of the cosmic rays. Then I'm going to introduce the main measurements, the main results of the Pierogi Observatory. After that, I'm going to say something about the interpretation of these results, especially the energy spectrum and the composition, in terms of a simple astrophysical model, a simple astrophysical scenario. Then I'm going to give some complementary information that we can gain from, for example, from the neutrinos. And also I will briefly say something about the improvement in this understanding from the study of the interactions in the source and during the propagation. I will then at the end just say a few words about the future prospects or the future wishes about the ultra-high energy cosmic rays and neutrinos. So let me just start by showing the cosmic ray energy spectrum, which, as you might see, is spanning over a wide, a very large range of energies, in which you can see that basically the behavior is very similar from low to high energies. We see that it has a power law behavior with some changes in the spectral index. We can also see that the flux is strongly decreasing while the energy is increasing. And because of these, different detection techniques are needed at different energies to detect these particles. So I'm going to focus on the ultra high energy part of this spectrum, which is above 10 to the 17, 10 to the 18 eV. And this is basically what you see on the right of the slide. It is basically a zoom of this plot where the flux is multiplied by some power of the energy. This is what is usually done in this with these plots, just to increase our ability to see if there is a change in the spectral index. So in this plot, you can see actually what is the comparison between the energies that these cosmic rays can reach, and what are the energies that can be reached in terrestrial accelerators. So just to show that these particles are really much more energetic than what we can get, for example, at LHC. So, okay, so basically what we might say already is that by considering the magnetic field and the size of the possible extragalactic sources, we can make some very simple consideration at the beginning and say that cosmic rays with these energies, like above 10 to the 17 or 10 to the 18 eV, should be extragalactic. One might also say that by looking at the previous slide, where we see that the behavior of the spectrum is similar at different energy ranges, we could say that similar acceleration mechanisms could work at different energies. For example, the acceleration thanks to the shocks which could be present in these astrophysical objects. So in the left of the slide, I'm showing what is called the Hillas plot, which is in this case some kind of classification of the sources depending on the size of the region and of the strength of the magnetic field, which we can use to estimate the maximal energy that can be reached in the accelerator. So one can see, for example, that regarding small sizes, let's say, one could reach some kind of very high energies in, for example, neutron stars, or on the other side of the plot, one could reach very high energies in, for example, galaxy clusters. So this is similar to what one can do if we think about the LHC and consider the size of the accelerator and the magnetic field at work there. So now this is, of course, I mean, I'm going to talk mostly about cosmic rays, but these are not the only messengers that we can collect from our universe. So we might imagine that in the same sources in which these particles are somehow accelerated and gain so much energy, in the same sources other cosmic messengers are produced, such as neutrinos or gamma rays or even gravitational waves. So this, for example, because we might think that in the same region in which we have the production of ultra high energy cosmic rays, we might also have some kind of photons or particles or matter with which this, for example, protons or charged cosmic rays could interact. And this might produce then pions, which in their decay could produce, for example, neutrinos if they're charged pions, or photons if they are neutral pions. I'm going to focus, as I said, in the charged cosmic rays. If these cosmic rays then are accelerated, they are able to escape from the environment of the acceleration region, then they before reaching our detectors, they for sure encounter some other things during their travel. So they could their direction could be deflected by the presence of magnetic fields, but they could also, for example, interact with photons that pervade all our universe. In particular, we consider for the cosmic ray interactions, the CMB, the cosmic microwave background, and the infrared fields. So this is what I'm going to focus now in the next slides on the cosmic ray interactions. So basically what we have, what I just want to say is just to consider for the moment a charged cosmic ray, so a proton, for example, and then I want to consider the photons, for example, of the cosmic microwave background. So in this case, if I'm just sitting on the proton that is traveling through the extragalactic space, I might see the presence of the photons, and I might which are very, very energetic. So this is simply understandable if we look at the relation in the light blue rectangle, in which I put the energy scale of the reaction, let's say. So basically, if we consider the energy of the photon in the proton rest frame, we have to deal with this multiplication of the energy of the photon taken in the lab frame with the Lorentz factor of the proton. So let's just try to make a very basic calculation. So if we take into account the typical energy of the CMB, like 10 to the minus 3 EV, and then we have a proton which has been somehow accelerated to, for example, 10 to the 19 EV, we might have in the proton rest frame, we might have enough energy to produce a pion. So we might have enough mass at rest. The same is if we take, for example, a larger energy of the photons, which could be, as it could be for the infrared photons, and we consider a smaller energy, a proton of smaller energy, we might be able, again, to have enough energy to produce a pion. And this is actually what happens. So this is one of the most important reactions that we have to take into account, like the photopion production by protons, for example, that through the excitation of the delta resonance, which is depicted here in this plot of the total cross-section as a function of this epsilon prime. So the first peak is exactly the delta resonance. Through this reaction, then the proton can lose energy, so about 20% of its energy, and then producing the pions, it can then produce also the neutrinos, which are the product of the decay of these pions. Okay, but then let's see what, so how this translates in the path that the proton can travel before having some probability to interact with the photon. So in this plot, I'm showing the energy loss length in megaparsec as a function of the energy of the proton. So of course, so this is actually the inverse of what I'm showing here in this formula, in which of course we don't take, as I did in the previous slide, we don't take exactly the energy of the CMB as what I've shown before, but we take the spectrum of the CMB and the cross-section of the photopion production, and then we see what is the energy loss length. So one can see already that, for example, at the highest energies, the most important reaction is the photopion production, while if I go to intermediate energies like 10 to the 19 or 10 to the 18 EV, what is predominant is the energy loss because of the photopion production of the CMB. What one has to notice is also that at the highest end, so in this energy range, basically in the entire energy range, it is very important to consider the CMB for the protons. And this is because the CMB, the density of these photons is much larger than the one of the infrared, for example, light. So how does this then translate in in what we see of the cosmic rays? So here I'm showing again the spectrum of the flux of the cosmic rays multiplied by the energy to the cube as a function of the energy. So this figure is taken from a very famous paper in which Berezinski and other authors explain very extensively the features of the spectrum in terms of interactions of the cosmic ray protons in the extragalactic space. So basically, the changes of the slope of this spectrum can be attributed to this interaction. So for example, the ankle, which is this change of the slope at more or less 10 to the 18.7, could be due to the pair production of the protons in the extragalactic space, while this, the energy losses, as I explained before, due to the photopion production could be the origin then of the strong suppression of the flux at the highest energies. So in this sense, we might be able to say that the end of the cosmic ray spectrum could be due to a propagation effect. And this was already predicted by Greisen, Zatsepin, and Kuzmin already in 1966 after the discovery of the CMB. But actually, there is evidence that cosmic ray at the highest energies are not just hydrogen nuclei, but they could be heavier than that. And this is on the left, this is the measurement of the, this is the observable that it is very sensitive to the mass composition, and I will explain this later. So if we have nuclei, actually what happens is that in a similar way as I explained before, so the nuclei interacting with the photons, for example, of the CMB, are just disrupted by this interaction. So what I'm showing here is the cross-section of an iron nucleus as a function of the energy. And in this case, we see that still the delta resonance, which is the one in orange, it is still present, but there is another resonance which is called giant dipole resonance at lower energies, which makes exactly what I said. So the nucleus can be disrupted in smaller fragments, including, of course, nucleons or helium particles. So then this also translates, okay, we want to see what happens then to cosmic rays suffering these interactions. So basically what we see in this plot, in which we have the energy losses of an iron nucleus in the CMB or in the EBL as a function of the energy. So we see that the energies at which before for the protons we had the photopion production, in this case, we have that similar length, similar interaction length is corresponding now to the photodisintegration of the nuclei on the CMB. While at intermediate energies, we have that pair production, which is the one in green, is competing with still with the photodisintegration, but now which would be now at intermediate energies on the infrared photons. So on the right, I'm showing the result of a simulation that we did with our code for the propagation of the cosmic rays. So we show on the y-axis the energy at Earth as a function of the distance of the source, and what one can see is that there is a depletion of nuclei in the same way that what happens to protons. So in some sense, what we see about the suppression of the spectrum at the highest energies, if we consider nuclei, could be due similarly to what happens to the protons, but this in this case could be due to the photodisintegration. So this is still this still could be considered as a propagation effect, but due to a different process because of the composition of the cosmic rays, which is unknown. Okay, so now after this brief introduction, I want to understand, or want to show what we can gain by using this, by exploiting these huge detectors, what we can gain about the cosmic ray characteristics. So I'm going to show some results, and I'm going to explain how these observatories work. I'm going to focus on the Pierogi Observatory, which is located in the southern hemisphere in Argentina. but I mean, the similar considerations are valid for the telescope array, which is located on the northern hemisphere. So the Pierogi Observatory is located in the region of Malargüe in Argentina, in the Argentinian Pampa. It is made of two, more than two, but actually these are the ones in which I'm going to focus, detectors, which are the surface detectors. These are more than 1,600 tanks, 1.5 kilometers spaced. And these are just water Cherenkov tanks. And they cover a surface of 3,000 kilometers square. These are overlooked by fluorescence detectors subdivided in 4 sites, which can work just in moonless nights, basically. Plus, we have an infill array of 60 tanks with smaller spacing, which means we can gain something at the lower energies. And the heat telescopes, like some telescopes that can work in a tilted way, so that they can basically look at the shower, not just next to the ground, but basically when the shower it is still developing in the atmosphere, or it looks basically at the showers which start to develop earlier in the atmosphere, meaning that they are less energetic. Of course, there are several facilities which monitor the atmosphere, and there is also the engineering radio array, which is now part of the main detector of the observatory. So in this slide, I just want to say something about the hybrid detection of the observatory and about the functioning of the basically of the experiment. So basically what is exploited is the fact that in this case, the atmosphere is used basically as the sensitive part of the detector. So the telescopes basically look at the fluorescence light that is emitted after the excitation, which is made because of the particles which are present in the shower, and they excite the nuclei, basically of nitrogen in atmosphere. So this light is basically recorded, and it makes what is called here the longitudinal profile of the shower. So this is basically just the energy loss, so exactly the energy loss in the atmosphere, which if you integrate that, you just obtain the calorimetric energy. So this is this X that you see in the formula is exactly the depth in the atmosphere. So it is measured from the top to the ground. And so this profile is d over dx as a function of the slant depth, which is measured in grams per centimeter square. On the other side, the SD, so the surface detectors, these water Cherenkov tanks, they basically collect the particles which arrive at ground. So they can give some kind of lateral distribution of the shower. And this is also very important because they are very sensitive to the timing of the shower, and the timing of the shower is also very important for the determination of the mass composition of the shower, because it is sensitive to the muonic and the electromagnetic part of the shower, which are strongly related to the mass composition. So basically the determination then of the energy is done, is based on the calibration of the experiment, which is just based on experimental data. It doesn't rely on models. So the variables, this S38 that you see on the y-axis is basically is the energy estimator of the SD, which and then we exploit this kind of correlation that you see with the FD energy, which is found by using hybrid events. So those events that are seen both by the FD and the SD. Okay, let's just come to the first result I want to show, which is the energy spectrum. This is the most basic, but the most important measurement of this observatory, which is the energy, the number of particles, basically, as a function of the energy. So the last update of this of the spectrum was given in recent publications on PRD and PRL this summer, and this is done with more than 215,000 events with the zenith angle less than 60 degrees. So there are no identification of declination dependence of the spectrum, but there is some identification of several spectral features that I also briefly introduced before. So what we see is that is a change of the slope already at 10 to the 5 times 10 to the 18. So the first one is called the ankle, and which I also anticipated before. At the highest energies, it is visible the suppression of the spectrum, which is already established since many years at 46 times 10 to the 18 eV. What is new is this feature, this change of slope at 13 eV, and then I will discuss later what could be the interpretation of this feature. Then let's come also to a very important variable, which is the mass composition, which is one of the unknowns of the cosmic rays. So of course we don't know the origin, we don't know the sources, but we also don't know what these sources are producing. So to do this, we try to use some, we try to extrapolate from the measurements some sensitive variables and try to explain them in terms of mass composition. So for this, we use some kind of simple model, like the Heitler model for the extensive air showers, which is on the right of the slide, which is basically some kind of analogy to the shower initiated by a photon. So in this case, if you look at every, so basically at every interaction length, basically the shower can be, you can imagine that it is split in two. And after this, at some point at depth x, you will have this 2 to the x divided by lambda, which is the interaction length. This is the number of nodes. So at the depth x, you can actually, you know what is the energy of the at that depth, which is exactly the energy of the particle, of the primary particle, E0 divided by the number of nodes of this shower. So then at some point you will reach a maximum number of particles in the shower. And this is the point at which basically the particles in the shower do not start anymore this splitting, they do not interact anymore, but they just lose energy because of ionization. So this is a critical energy that you reach at some point in the development of the shower. So if you want to know how many particles are at this point, you just have to, or if you know the primary energy, this is the E0, the primary energy divided by this critical energy. So the energy at which the particle is just losing energy because of ionization. So if you want to know what is the point in the atmosphere in which you have the maximum number of the shower, basically this is strongly related to the energy of the particle. So if you look at this relation, so the X max is proportional somehow to the logarithm of the E0, of the initial energy. So basically the shower will have its maximum number of particles deeper and deeper in the atmosphere depending on the energy. And then in a similar way, we can also consider what is the relation with the mass. So if we think that the shower is not initiated just by a proton, but by a nucleus, so if we have a proton with energy 0, then we can imagine similarly that we have, for example, a nucleus, which is composed by A nucleons, each of them with energy E0 divided by A. So that means that, of course, in a similar way, this shower with this E0 divided by A energy for each nucleon will start to develop much earlier in the atmosphere. So in this way, we can find a relation of the X max, so the maximum number of the particles, so the level of the atmosphere in which we have the maximum number of particles as depending strongly on the mass. And this is actually what is done. For example, in this slide, I'm reporting some data in the black points, some data from the showers, which are compared to simulations of protons and of iron nuclei with the same energy. So one can see easily that, for example, the iron shower with the same energy will start to develop earlier in the atmosphere. So basically the value of the x-axis, which starts from the top of the atmosphere, is on average smaller than what you find for the proton, because of what I said before. Another thing that is clear is that the fluctuation of this of the point at which this distribution reaches its maximum is not really fluctuating a lot for the iron, and this is because in the iron shower there are much more particles than in the proton shower. And this is then translated into taking into account these distributions and then the moments of this distribution. So the first one is the average, so the average point at which the shower reaches its maximum. So this is the min X max. And the second moment, which is the width of the distribution. So this is what comes out from this from the measurements. So the measurements are the black data points, the black points, and these are compared to expectations from models in the red and the blue lines. So what one can see is that the min X max has a break at the energy of the ankle, more or less, while it is clear that the fluctuations, the sigma of X max, are decreasing with increasing energy. So we will see later what this means in terms of mass compositions at the source, because this is what we actually observe at Earth. So just a few information. I'm not really the most expert in this, but it is very relevant to say, of course, that a lot of effort is done also in the understanding of the arrival directions of the sources. So what I'm showing here is the mapping galactic coordinates of the flux of particles about above 8 eV, which shows the presence of a dipole, and also the magnitude of this dipole has been studied, and this both the magnitude and the direction of the anisotropy support the hypothesis of the extragalactic origin of this dipole, of the cosmic rays. Moreover, also some comparisons with the directions of the cosmic rays to catalogs, to existing catalogs of sources are also done. Like, for example, this has been done with the Fermi-Lat sources about within 250 megaparsec, assuming that the cosmic ray flux coming out of these sources is proportional to the photon flux, and taking also into account the propagation effects due to the interactions in the extragalactic space, one can find that the maximum signal by scanning the angular distance and the energies of these events is found for 38 eV. So above 38 eV for the sample of the starburst galaxies in these catalogs. So these are just, I mean, some basic information that we have from the Pierogi Observatory. And I think I can stop here. I can do a first stop in case there are questions, urgent questions about what I said before. So
let me start with one question. For a long time, there was this apparent disagreement between the mass composition claims from Auger and the telescope array. The telescope array was favoring more lighter composition than Auger. But then I think there was some kind of agreement. Is that still the case? Has that moved forward in the right direction?
I think it is still okay. I think I have, since I'm not going to talk about this in the next, I think I can use one of my slides in the backup if you want. So yeah, okay. The telescope array is presenting, let's say, the results on the composition in a slight different way from what Auger is doing. So the final statement about this analysis is that these are compatible within the systematics. So that's fine. I mean, there is still compatibility between the two experiments, and there are working groups, joint working groups in the collaboration. So people from Auger and people from TA who work together to understand this. But still, I mean, the way maybe it is presented, it is slightly different. For example, TA, I think, is using interaction models like the QGS jet, which is not used anymore by Auger, which is somehow excluded by the sigma measurement of Auger. It is also true that a direct comparison is not easy to do. So you cannot just take these two plots and put them on top of each other, because the analyses are different. So the TA1 is still biased by the detector acceptance. So basically what they do to put them on the same plot is to redo the Auger analysis with the TA1 or vice versa. This I don't remember, but it's not just that you take the points and put them together. So there is some reprocessing to do this. Yeah.
Okay, thanks. We have any other question there?
So just on the last slide you've shown, not this one, but the one preview, the one that you had just before the questions, actually.
Yeah.
Choose. So just to understand on the plot on the right with the test statistics, so it's the threshold energy is a lower threshold or is a upper threshold?
This is energy of the events, of the cosmic ray events that you are considering. Okay, so basically the signal is found for events above this 38 eV.
Okay.
And then, of course, this is not the only quantity that you have in your analysis. There is also, of course, the angular distance from the source. So you take into account. So this is basically a scan. I'm sorry, I don't have the plot, but this is a two-dimensional plot that you can find in the JCAP paper, which you have on one side the angular distance and on the other side the energy.
Okay, I will try to find it. No worries. Thank you.
All right, I see no other raised hands or comments, so I think we can go on, Denise.
Okay, so now I want to focus on the interpretation of the data. So I've just shown the energy spectrum and the composition observables, and then I want to try to put them together to see what we can understand about the cosmic ray characteristics. So so just to start, one has to use a very simple model. So basically what is done is to use identical sources distributed in the universe in an easy way. And then we consider them, as I said, equal. So basically they all emit the same power law spectrum, which is this e to the minus gamma. And they all have the same behavior in terms of acceleration to maximal to a certain energy, and they have this. And we also assume some rigidity dependence. Then, so this is the assumption that we make. Then we have to take into account the extragalactic propagation. So we take into account the extragalactic photon fields. so the infrared models and the CMB. And then, of course, also the input from the nuclear physics. So we have to take into account photodisintegration and photopion production and all the things that this imply. At the end, we want to reproduce the spectrum and the composition data and see what these parameters like the spectral index, the rigidity cutoff, and the mass composition, so the species that come out from the source. So we want to see what we find. Okay, so putting this all together, then we can find some kind of configuration for these parameters. And here I'm showing the projection of these fit results on the parameter space on two parameters, like the rigidity on the y-axis and the spectral index on the x-axis. So this the colors indicate the best fit, so which is found for a very small value of the spectral index and very small value of the rigidity. So that means already, and we will see later, that so what I said before about the possibility that the suppression of the spectrum is due to a propagation effect, this is a bit, so now this is a bit challenged. So, but let's see what is then how the spectrum and the composition are described at the best fit. So basically what I'm showing here is with the brown line is the best fit, is the whole particle spectrum at Earth, subdivided with the colors in several mass groups. So what one can see already is that the green group, which is basically the CNO1, is predominant. In the lower plots, you can see the composition variables like the average Xmax and the sigma of Xmax, which are described above 10 to the 18.7. So the fit is done above the Encke energy. So in this other configuration, I just want to highlight what is the contribution of the different particles of the different species from the source. So in this case, the green line is means the nitrogen, for example, the CNO at source, together with all its secondary particles, so down to protons. So nitrogen during the propagation is producing smaller and smaller, lighter and lighter masses down to protons. So this is really a very predominant part of the spectrum from the sources. So now I want to explain very briefly, because the implications would need a lot of discussion, but the implications on the source characteristics of the parameters that we have found. So first, we have found a very low value of the rigidity cutoff at the sources. So what I said before about the interpretation of the suppression as due to the propagation effect, now it's not really so exact. So basically now we find values of the maximal energy at the source, which are very similar to the threshold of the reactions that I was describing before. So basically in the end, it is possible that the suppression of the spectrum is due to a combination of effects, which is not just the propagation in the extragalactic space, but also some kind of lack of power at the source. Another very relevant consideration is the one about the small spectral index, which is actually at odds with the theory on particle acceleration. So what we find is a much harder spectral index with respect to what is, for example, from the Fermi mechanisms. And this could be actually an effect of the escape of the particles from their sources. So basically what we see is not exactly what is accelerated in the sources, but it could be already reprocessed inside the source. And it could be that, very roughly speaking, but of course it is much better explained in this paper that I'm mentioning here. It could be that, of course, high energy particles. For high energy particles, it's much easier to escape than for low energy particles. So this could then give the hardening of the spectrum at the escape from the source. Then now I just want to show the very important thing, which is kind of, I think it's very difficult to explain, but I want to show that the use of the composition observable is not just important for constraining the composition, but also for the spectral parameters themselves. So here I want to show, and this is just an example, it's not fitting the data, the case at which we have at a fixed energy 50% of hydrogen and 50% of iron at the source. So in the left plot, I'm showing in blue the iron at the source, while the red is the hydrogen. In this case, I'm also taking a very small spectral index and a very small rigidity cutoff, which means that the proton, basically the blue line, which is the iron, has a cutoff which is 26 times higher than the one of the proton. So we are just fixing the rigidity and not the energy. So that means that we are in this region of the parameter space in which we have both a small spectral index and a small rigidity cutoff. So this is, I mean, it's not, of course, optimized to reproduce the data. This is just an example. So then this is what comes out from the source, which is then reprocessed during the propagation. And then what comes out in terms of composition is what we see on the right. So it is basically the behavior that we see on the minix max is going from light, so from the red, to heavy, while the energy is increasing. So the behavior of the sigma is this abrupt change, which of course is not exactly what is reported on the data, but this is just to show that the lack of superposition of the spectra at the source means that at Earth we see some kind of decreasing of the sigma in the composition. So now we want to see what is the opposite case. So this is in the magenta rectangle in the plot of the parameter space. So in this case, I have a high spectral index and a high rigidity, which means that for a high part of the energy range that I'm considering, the spectra of the protons and of the iron, which are accelerated at the source, are superimposed to each other. So this is, of course, what escapes from the source. Then you have to reprocess that and then then come at Earth. So what is reported then in the composition is, of course, some intermediate composition between iron and hydrogen. So this is, as I said before, this is the behavior of the X max, the min X max as the behavior of the logarithm of the mass, while the sigma is actually, the expected sigma in this case is actually exceeding the fluctuations that are predicted for hydrogen. So basically what I want to stress with this example is that the sigma of X max is a measurement of the spread of the mass composition, which is can be due to different things, can be due already to a mixed composition at the source. So the source could accelerate already some mixed, several species, which then do what I explained. But this can be done also because of spectral parameters. So in this example, you have seen how the same composition can give different expectation for the sigma. But this can be also due to the propagation of the cosmic rays in the extragalactic space. So I could have just, let's say, sorts of just irons. I don't know if this is possible, but then the propagation in the extragalactic space could give a spread of the mass composition, which could translate then in some sigma, as I'm showing here. So then much more in a much more simple way, we could also make some considerations about the composition of cosmic rays. So if we see nuclei at Earth, they should exist somewhere. They should be accelerated in some sorts. And if they are there, they should survive the interactions which they could suffer because of the presence of matter or of radiation. So the survival condition can be satisfied depending on the characteristics of the source. So let's say if a source is very dense, if there is a lot of there are a lot of photons, of course, the interactions are more efficient. So if I have a nucleus, it is very probable that this is disrupted, very roughly speaking. So, for example, in this kind of calculations, we have considered the possibility of the interactions of this of nuclei within radiation field of a gamma ray burst, in which we assume to have at the beginning just a production of ions, which is, of course, I mean, it is just as an example. We are not saying that GRBs accelerate only ions, but this is just to show that by going from the left to the right of the slide, and by increasing the luminosity of the environment, and by letting the, let's say, the system go to the end of the development of the shower, then we see that we see how the energy which is present in the first accelerated nuclei is transferred possibly to the secondary nuclei. So we can see that by increasing the luminosity, so by increasing the density of the radiation, the energy is much more transferred to lighter particles, so in principle to protons and neutrons. So it means, this is just to say that in case nuclei are actually accelerated in sources, then if we observe them, it means that somehow they also survive within the source. So there has to be a balance between the interactions in the source itself. So I'm not an expert about which sources could provide a mixed cosmic ray compositions. There are several studies, and this is of course not a complete list of them, and these studies go from neutron stars, Wolf-Rayet stars to blazars. So there are also some implications, as I said, that we can understand from mixed cosmic ray composition on the understanding of the effects of the features of the spectrum. For example, the ENCOL could not be interpreted as a propagation effect of the protons in the extragalactic space due to the pair production, since if we have nuclei, we have seen, and as we can see also in this plot, that at intermediate energies, the pair production is not the most relevant process. Other possible explanations are the signatures of in-source interactions, or maybe even the interplay between different contributions of different populations, like it is explained in this paper. Now, I just come for a while to the new feature at 13 eV. So this new change of slope of the spectrum, which is described in the PRD and the PRL paper. This actually might reflect the interplay between the contributions to the flux of the helium and the CNO components injected at the source. So what I'm showing in these plots is with the brown line, the all particle spectrum, but in the two plots, I'm just showing separately the contribution of the primary nuclei. So basically the green line, the green dashed line on the right is basically the total contribution of the primary nitrogen plus all its secondaries. On the left plot, I'm showing with the dashed line, with the dashed gray line, the primary contribution of the of the helium together with its secondaries. And this is, by the way, this is not even dependent on the cross-section model that we use for the propagation. So it could be that this this feature is due to the propagation effects. So now I just second, so I just want to stress that, of course, the Pierogi Observatory has not been designed for the search of neutrinos, for example, but it is also possible to look for neutrinos with inclined showers with the ST, for example. So similarly also for the photons. So limits for the observation of cosmogenic neutrinos and photons are given in these papers, and there are also several searches for neutrinos in coincidence with the transient events. This just to introduce the importance of considering together different messengers like the cosmic rays and neutrinos, which are strongly connected by the fact that neutrinos which are produced in protons interactions carry on this 5% of energy of the proton. So actually, due to the heavy mass composition of the cosmic rays and the spectral characteristics of the cosmic rays at the source, the expected cosmogenic neutrino flux is below basically the current limits, and we don't know about the future. I mean, there are a lot of studies on that. Within the UHECR collaboration, it has been done some kind of optimistic prediction for the future, let's say, in which basically the sensitivity of the neutrino fluxes coming from proton primaries is given in the parameter space of the, let's say, considering the distribution of the sources, so the cosmological evolution like this M and the maximal redshift that you consider for the sources. So in this case, it is really important to be able to discriminate what is the amount of protons that you can see at the highest energies. And then also, I just want to stress that basically, it is also very important to consider the models in which interactions can happen also in the source. So in this case, there is a way also to explain, as I said before, the ankle, so the change of the slope at 10 to 18.7, thanks to the interactions that can happen in the source. And also this gives in some cases, like the one I'm showing here, the low luminosity GRB, for the low luminosity GRBs, this can give also a way to explain the astrophysical flux measured by IceCube. I'm just showing here on the right some papers in which these source propagation models are exploited to show what is the result, both in cosmic rays, in neutrinos, and in photons. Okay, just a few words about the future. So Auger and TA are planning and are already developing some improvements. In particular, for example, Auger is going to, it is already working on this, putting the scintillators on top of the water sharing detectors to discriminate better the muon and electromagnetic component of the shower, to isolate better the proton component at the highest energies. So, of course, there are also other experiments planned for the future, like the exploiting the radio detection of inclined air showers, like for GRAND, and the planning also for the observation of air showers from the space with POEM. So with this, I just come to my conclusions. I'm sorry, maybe I was very long. So, I mean, the open questions that, I mean, these are still there. So, of course, we want to know, or we want to understand what is the origin of the flux suppression and of the other spectrum features. I've just shown what is the effect of propagation or source issues on the spectrum. maybe also in-source interactions are important for the description of the spectrum itself. It is very important to understand what is the proton fraction at the highest energies to see if there is any possibility still to do some charged particle astronomy. And considering together also the other messengers like neutrinos and photons, it is fundamental to have a better understanding of this. I didn't have time to talk about the hadronic interactions, but this is also a very important issue, which is totally open. So being able to discriminate the muonic component of air showers will also help us in the understanding of air shower physics, which is actually the place in which these interactions can reach so high energies that they cannot be reproduced in accelerators. So for the future, we of course wish to have higher statistics for cosmic rays and better composition sensitivity, but also we would like to have multi-messenger studies, both from the theoretical and experimental point of view. And this also the hadronic interaction point, which I could explain, is also, I mean, a future study, of course. So thank you very much for your attention. And if you have questions.
Thank you very much, Denise. Let's see if we have questions in the audience. Just unmute yourself and ask, or write it if you can.
So I have a short question. Can you come back, please, on the, because I forgot that actually the explanation of the uncle with the deep model, the fact that it doesn't work. I didn't. I don't remember the explanation.
I don't know if you wanted to say maybe this, to see this again. I don't know.
You know, the deep, yeah, like you were saying at some point, like here, the Euclidean curl, you cannot reproduce it with just protons, just from the energy losses of the protons or something like that.
No, okay, it is the opposite. So basically, if you have just pure proton composition, what you expect to have as interactions in the extragalactic space is the ones I'm showing here on the left plot. So at the highest energy, you have basically you lose a lot of energy because of photopion production. So every time you have a photopion production, you lose more or less 20% of the energy of the proton. While if you are at intermediate energies, like 10 to 19 or below, 10 to 19.5 or below, you basically have a very large interaction length, about hundreds or megaparsecs or gigaparsecs. And this is the place where basically the universe is, I mean, how to say, it's not depending on local properties of the distribution of the sources. So this region of the energy of the spectrum is quite somehow fixed. I mean, it's if it is due to protons, it should really have that shape. Okay, so if it doesn't, or if it is not protons, it is really difficult to. I mean, you cannot explain that with per production energy losses. So I don't know if it was exactly your question.
Okay, no, but it's okay. It's okay. Thank you.
So basically, if you have nuclei, it's much more difficult to explain. But since this is probably what is happening, it's that energy have really a mixed composition. You cannot rely on the fact that you just see the per production.
Okay, that I understand. Okay, thank you.
So I have a little question. I would like to ask you if you can say something on how can we understand the redshift distribution of sources, which is the effect on the shape of the Hankel spectrum we can observe, and if this might induce a degeneracy in the way we study sources of these ultra-high energy cosmic rays.
Okay, let me see. Okay. For example, this could be useful. The redshift distribution of the sources, I mean, it does make a big, effect for ultra high energies, meaning above, let's say, the ankle. So actually, in order to see already some effect of the distribution of the sources, so maybe this is not the exact, so you should go below the ankle, in which you start seeing the effect of the redshift distribution, which could be very simply, for example, like 1 plus z to some power. So to that cosmological evolution that I was trying to show with the neutrinos. Okay, so with the cosmic rays, actually, you would see some difference just below the part that I'm fitting here. So below 10 to the 18.7. So basically, as soon as you increase the power of this term, so 1 plus z to some power to some m to this power, you will see an increase of the flux at the lowest energies. So this is just because, I mean, if you increase the power of this function, you have a larger density of sources in the far universe, which means that this flux from these sources is slightly increasing. But this is not the most important, let's say, effect, because the effect is much more visible in neutrinos. So you would be able to increase the neutrino flux that you see here. So as soon as you increase the density of the sources which are far away, you also increase the neutrinos. And the same increase you are not able to see, or it's not so efficient in cosmic rays because they lose energy. So one way to better constrain the redshift distribution of the sources is to look at neutrinos. Then, unfortunately, the point is that what we find, for example, from the models that we are using to fit the data of the cosmic rays, is that the maximal energy of the cosmic rays is very low. So this is bad for neutrinos, because if you don't have enough energy, you don't produce a lot of neutrinos. And that means we don't have enough cosmogenic neutrinos to see this effect. The help could come from the possibility that, or from the allowed proton fraction that we could see at the highest energies, because in this case, so protons can produce more neutrinos than nuclei, and then we might have some higher neutrino flux. So I don't know if this answered your
Yes.
questions.
Thank you.
We have time for one final question from the audience. I don't see any hands. Don't be shy. All right, I'll jump in because I'm very curious about something. Unless John, did you have something?
Go ahead if you have a question. It was
okay.
Yeah.
So I was very curious about the fact that now it's very difficult to tell apart the effect of the GCK suppression and the source high energy suppression. So what, if anything, would you need to break the degeneracy, or just know what fraction is being contributed by each one of the two effects?
That's actually, I think, the first science case for the Auger prime. So that's a very good question. So I think a better determination of the composition at the highest energy would really help in this. So the effort of having a better discrimination between the electromagnetic and the muonic part of the shower, which is the most sensitive thing to the composition, would really help in this. So that's fundamental. And then also, as you see, basically here, so what is needed is really, I mean, the energies at which the FD composition is arriving is not exactly the energy of the spectrum where we have the last event. So this has to put together with the mass composition which is coming from the SD, which is also I mean, which can go to higher energy. So this combination would for sure help in this determination. But the joint analysis with the neutrino with the neutrinos would really also be important. I mean, we have this problem that yeah, the energies are not so large, so it is very difficult to disentangle that.
So currently, at least for measurements using only cosmic rays, the limit in the measurement comes from the uncertainty in X max, the composition.
You mean for what? For the
to determine the contribution of the GCK suppression and the high energy suppression, explaining the high energy features of the spectrum.
Well, it is of course in the big errors that you have at the end of the spectrum. So of course you would need much more statistics in that.
Okay. All right. Well, we should probably stop here. I want to thank you, Denise. It was great. It was a great review and also a great overview of the latest results. Thank you so much for making the time to talk to us. And thank everybody for being here. I hope we can have you here in person once all this craziness is over. And for the rest, yes, for the rest of us, we'll see each other in the next seminar in a couple of weeks. Thank you so much, everybody.
Thank
Bye
you.
bye.
Bye.
Thank you.
Bye.
Ciao, Denise.
Bye bye.